All right, welcome. Today, we're jumping into a kind of digital laboratory. It's called computational chemistry, a field where scientists get to explore the atomic world, not with beakers and test tubes, but with some seriously powerful computer simulations. Let's get right into it.
I mean, that sounds like something straight out of science fiction, right? But it's actually one of the incredible promises of this field. How is it possible to test millions of potential new drugs, or figure out exactly how a protein folds, or even design a brand new material, all from your computer?
Well, the answer is you simulate it. You build a digital version of these molecules, right down to the atomic level. Computational chemistry gives us the power to solve really complex chemical problems by creating these incredibly detailed models of tiny, tiny systems.
To do this, scientists have basically developed two completely different playbooks, two totally distinct ways of looking at the world. On one side, you've got the classical world, and on the other, you have the quantum world. And understanding the difference between these two, well, that's what this whole explainer is about.
So first up, let's explore that classical approach. Honestly, the easiest way to get your head around this is to just imagine you're building with Legos. It's fast, it's efficient, and you're just following a set of pretty simple, predictable rules.
This Lego world has a formal name. It's called molecular mechanics, or just MM for short. And it's built entirely on the physics of guys like Isaac Newton, classical mechanics. It figures out the forces between atoms using rules we can all kind of wrap our heads around, like gravity and springs. And the whole model works because it keeps things really, really simple. Atoms, they're just treated like little balls. The chemical bonds that connect them, imagine they're just tiny springs. And this is the most important part. The incredibly complex dance of individual electrons is completely and totally ignored.
So you might be wondering, why on earth would you use such a simplified model? Well, it all comes down to one massive, game-changing advantage: speed. By ignoring all the complicated stuff with electrons, calculations are just ridiculously fast. This lets scientists simulate enormous systems, like an entire protein, which would be literally impossible any other way.
But here's the catch, and it's a big one. Because you're ignoring electrons, you can't answer any questions where the electrons are the star of the show. Things like a chemical reaction, that's impossible to simulate with this model, because that's all about electrons moving around. So for all its speed, this model has a huge blind spot.
And that, of course, leads us to a really pivotal question. What happens when the very thing you're ignoring, those electrons, is actually the most important part of the puzzle you're trying to solve? What do you do then?
Well, you enter an entirely new world. Welcome to the world of electrons, the realm of quantum mechanics, or QM. If MM was like building with Legos, think of QM as 3D printing a model, atom by single atom, capturing every last detail. See, unlike MM, quantum mechanics dives headfirst into all the weird and wonderful behavior of electrons. It treats them not just as little particles, but also as waves, and it specifically tracks how they're arranged and how they interact with each other. The master recipe book, the fundamental set of rules for this entire quantum world, is the famous Schrödinger equation. Now, you don't need to know how to solve it, but you should know that everything in QM, from a molecule's energy to all of its properties, comes from finding solutions to this one equation. Now, quantum mechanics isn't just one single tool. It's actually more like a whole toolkit, and it's filled with a range of different methods. Each one offers a different balance between getting the answer exactly right and how much computer power it's going to cost you. Inside that quantum toolkit, you've basically got three main flavors. There's ab initio, which is the purest, most fundamental approach. Then you've got density functional theory, or DFT, which is a super popular middle ground option. And finally, there are semi-empirical methods, which are really built for speed. So on one end of the spectrum, you have ab initio. That's Latin for from first principles. These methods are built from the ground up, using only theoretical principles, no experimental data needed. Then, on the complete opposite end, you have these semi-empirical methods. These take a shortcut. They use a simplified theory and then patch it up with data from real-world experiments to get answers way, way faster.
Okay, so we've got these two different worlds, the fast, simple, classical world and the super detailed but very slow quantum world. It's time to put them head to head. And this brings us right to the core trade-off in all of computational chemistry, this constant battle between speed and accuracy.
This table really lays it all out. When it comes to handling electrons, QM is explicit. It deals with them directly. MM just ignores them.
For calculating energy, QM has to use that complex Schrödinger equation, while MM uses a much simpler function based on where the atoms are, and the final result for computing time. QM is extremely time-consuming, while MM is incredibly fast.
And to really put that in perspective, just look at this. If a molecular mechanics simulation takes, say, 1 unit of computer time, a comparable quantum mechanics simulation could easily take 100 or 1,000 or maybe even millions of times longer. I mean, the difference is absolutely massive.
So, with a difference that huge, how does a scientist actually decide which method to use? Well, it all comes down to picking the right tool for the right job. You're going to use the Legos or molecular mechanics when you're looking at the big picture. It's perfect for things like finding the most stable shape, or what scientists call the conformation of a molecule. It's also pretty much the only way to study the large-scale movements of massive systems, like watching a protein fold. For jobs like these, the speed of MM isn't just a nice bonus, it's an absolute necessity.
So here's the key takeaway. The choice is never about which method is better overall. It's always a strategic decision. A scientist has to balance the size of the system they're studying against the level of electronic detail they need to actually answer their specific question. And that brings us to our final thought. We've seen the two worlds of simulation as they are today, but, the technology that makes all of this possible is constantly evolving.
And this leaves us with a really fascinating question for the future. As our normal computers get faster and a whole new generation of quantum computers starts to come online, what happens to this trade-off? Will we one day be able to simulate a drug interacting with a protein with perfect quantum accuracy, all in real time? Will that line between our digital simulation and physical reality start to blur? That is definitely something to think about.